Good evening, everybody. Welcome to the April meeting of the Seattle Building Enclosure Council. As you probably know, the Seattle Building Enclosure Council is a nonprofit organization that's looking to promote the advancement of building design and construction, focused largely in the Northwest. My name is Nathan Sini. I'm an architect at Morrison Hershfield and the CBEC president. We have a strong board, including Amelia Davis, our secretary, Jeff Didion, our treasurer, Sharon Libby, our education chair, Clifford Marvin, our membership chair, Hillary Roy, our venue coordinator, Joel Thornburg is our sponsorship coordinator. If you're interested in sponsoring a future meeting, reach out to George. Bill Fordarson does our student outreach. Grace Wong does our communications. Jeremy DeWitt is our website chair. Penny Short is the board administrator. And while Sharon is on leave, Amanda Prott is our education chair. So if you have ideas for future CBEC presentations, please reach out to Amanda. Our next meeting will be in May on the 20th, presented by Jeff Speart from 4EA, formerly JRS, and it will be on the topic of amenity spaces on conventional roofs. We had a number of applicants for our scholarship again this year, and we've selected Lorena Ware from the University of Washington and John Brown from the Washington State University to be our scholarship recipients this year. John and Lorena will join us next month and our meeting, and we'll hope to acknowledge them then. A couple other events in the area. The CSI Puget Sound has a glazing fireside chat on 4/27 from noon to 1. And then also NIBS is having a Best Fest instead of a Big Best conference, a virtual meeting on 4/28 from noon to 4. You can check out NIBS for more information on that. Mostly just here to open the door for the dog. The WAGD Andis Symposium on Building Science is going to happen in September. It's put on by the Boston BEC and the Boston Architect Society, Boston Society of Architects. I don't know, they're basically the AA, but they're just in Boston. They've just closed their call for abstracts, but I'm sure that will be a great day of conversation. And next up, we have our sponsor, George Pettibone, with his aqueduct window subsill.
Hi there. I'm George Pettibone. I live here in Des Moines, Washington. I've been in the commercial glass and aluminum business for over 48 years. Started out with the Conair Company here in the Seattle warehouse in Aquapolis. Worked at Elite Railings and Windows for Honolulu for the last 7 years as a consultant. While at Elite, I developed the aqueduct subsill system concept, and we went for patent, and the patent attorneys were having a difficult time for us. So we put together a plan and finally got it patented. The attachments that are being shown now on screen are my actual announcement of this thing, because COVID-19 has made it very difficult. So Joel is going to flip through some of these things, or Nathan, and help us take a quick look at my introductory thing. It's too much stuff to try and jam into 5 minutes, so we just say this is the packet. That's the second page indicating the inclined plane of the water. This is a water drainage subsill. It's an isometric sketch of it completed with end dams. The next one, figure 6 coming up, is an isometric of a shortened up version for smaller windows, and the depth of it is basically the same thing. The inclined water trough that runs down below there is what makes it a patented item and separates it from the base plate. On page 7 coming up In the next slide is a nice little shot of one. We use this one for 2-inch windows made by Arcadia. And it was going to be done on a big building and it didn't quite get it. So all we have is a die drawing at this moment. The next slide will show you a conventional 4.5-inch storefront sitting on top of the aqueduct system. And the reason for getting it so waterproof, so foolproof, is that there's holes in the top to screw the window down to the top of it. There's holes in the bottom to screw the base plate down to the building structure. The two are entirely separate, entirely different. They can be engineered as big as a 1/2 inch diameter if necessary to bolt the base plate down. It can be cantilevered on top of a narrow concrete wall. It can do all kinds of stuff, but with the end dams and the wet zone and dry zone separation, the water goes in, the water goes out, the water goes down the front of it and goes out into the airspace. The patent was finally awarded in 2018. A separate 2019 patent was issued for the same basic concept with some minor changes to the wording. This is an isometric of the end cap, which has 5 screws to hold it tight on there. It's all caulked. After you put it on, you caulk the top of it and caulk the bottom of it, silicone. The next slide is an isometric of it. The base plate gets bolted down first. The inclined water plane goes on second and interlocks with the L-shaped piece on the base. Then it rolls over the backside, locks down. Then the sieve plate up on top has multiple large holes to drain water so that any water that gets in there drains automatically into the inclined plane. And no one is allowed to put any holes in the inclined plane. Overall, a major sized building could save 8,000 to 10,000 holes drilled in what is supposed to be a waterproof subsill of previous designs used for the last 25 years. With having absolutely no holes in it, we've done a 22-story building, an 18-story building, a 15-story building, and a 6-story building. All of these buildings had tremendous water damage, tremendous fall repair, tremendous paint peeling off of the building, and we solved it all with the GP 1000 part number that we used over and over again, which is now the aqueduct subsill system. I've revised the word aqueduct, and I just really think it might help in marketing. Having these buildings, this one is 1 block from the ocean. This is a 9-story hotel, and we put all new windows in it with Arcadia windows. It all works absolutely fine with pounding rainstorms in Honolulu. The next one is a close-up of a window. This is the Arcadia window on a high-rise hotel. We had an old-time set of windows with a plaster wall, giving us a tremendous problem with trying to get the old window out and was damaged all the plaster. So we used the longest leg on the outside that we could and left the old windowsill in. That was captured, siliconed up, and the point of the whole thing stopped all the water leaks in this. This is about an 18-story hotel. The concept has been proven. We have approximately 14 buildings in Honolulu, starting in 2014 till now, and they don't leak. It was tested by CCL West Laboratories in California. We got a test report for them with an old airplane motor and a giant propeller at 276 miles per hour wind velocity. And we almost doubled the water leakage performance of the Arcadia sliding windows. From its routine 9-pound water test, we got it up to 15 pounds. So we're quite proud of this product. Not to say that it's not been done before in some manners, but none of them eliminated the problem of drilling holes in your brand new subsill and hoping that somehow you could cover it up with silicone and somehow it wouldn't expand and contract in a 22, 23 foot long one-piece subsill. This subsill is unique in that it is not technically bolted down to the building. It's interlocked with the base plate and the upper incline plate, and it can expand and contract horizontally without harming itself. And it will last for a lot longer than anything that we think is out there. We did an awful lot of this with Janney Elsner, the biggest, most prestigious architect in Honolulu. They helped us to design some things into it, and they gave us parameters, and I invented it, and my patents on it are because it is totally unique and it will not leak. It's been water tested in California. It's been water tested on a 22-story high-rise with Janney Elsner testing it over and over and over again for water leaks. So I'm quite happy with the thing. Now I need to try and figure out how to get it into a business plan, get it into some warehouses, and get it sold all over America. I appreciate your time and your interest, and I'd be glad to answer any quick questions if anybody has it. That's the short version of about 8 years struggle to patent this. Thank you very much. Any questions? I'd be glad to answer anything.
That was great, George. We'll be using the Q&A feature throughout the presentation for audience questions. So if you would like to type something in there, we can get that over to George to answer. But thanks again for your sponsorship. Sponsorships, keep our Zoom license up and running, and we're really glad to have you.
All right, I'm very, very pleased to be able to get in front of the people at this elevated level in the architectural field. I hope everybody finds it quite interesting.
Thanks, George.
Thanks.
Now I'd like to introduce our topic today, which is window, curtain wall, and skylight condensation problems and solutions, which is presented by Sean O'Brien from Simpson, Gumpertz, and Hager in New York. Sean is a senior principal at SGH, where he's worked for almost 20 years, and is also a fellow Beck chair, co-chair in New York. Sean, please take it away.
All right. Thanks, Nate, for that introduction. So Sean O'Brien, I'm actually a mechanical engineer by education who kind of randomly stumbled into this field and turned out to be a pretty good match. So I've been doing this for about 20 years. I was originally hired to look specifically at building science issues. At the time, Massachusetts was the first state in the nation, it was 2001, to implement air barrier requirements in the building code. So there's a big push for building science. So that was kind of my start. And a lot of what I'm going to show here is experience over the past 20 years looking at condensation issues. This is AA accredited, one learning unit. Nate, I'm assuming will let people know how to give their information so we can get you guys credits. And we're going to go over just a couple of basics, kind of the fundamentals of condensation, how it happens and why, and then look at case studies because it's always good to see how this stuff works in context. Right? Here's a real building, here's a real problem, here's a real solution, and then go over some remediation strategies. Ideally, we want to get this right the first time in design and not have to come back, but I'm sure many of you have been in that situation of getting called in after the fact to try to resolve a problem. So we'll go through some of those. So condensation, quite simply, is water in the gas phase that reverts back to a liquid when it hits a cold surface. That's the simplest definition I can probably give. Moisture in the air condenses out somewhere. Take a cold drink out on a hot day and you condense on the outside of it. Right? In colder climates, when it's fairly cold out and you have moisture inside, you condense on windows for the same exact reason. The point where you condense is known as the dew point. So this is the temperature where moisture in the air will condense out. And I'll go through how that's calculated in a minute. But dew point is also a measure of the absolute amount of moisture in the air. So a higher dew point always means more moisture. And if you know the dew point temperature, or rather just the dew point of a space, what your conditions are, it's a simple design matter of saying, here's my window. If the temperature drops below the dew point, it condenses. If we stay above it, we don't. So relative humidity is another concept related to this that often comes up. You know, people will say the relative humidity is too high or it's too humid in here. But the tricky thing about relative humidity is it's a moisture content measure, but relative to saturation. So if you look at these three boxes representing samples of air at different temperatures, the colder sample of air can hold less moisture than a warmer sample of air. So in this case, we have three different temperatures. We have the exact same amount of moisture in each sample, but the relative humidity is different in each one. So at 50% humidity or at 50 degrees, you're about half saturated. When you go up to 70 degrees, your capacity or your saturation point is going to go up. So the humidity is actually lower. And then at 85, it goes down even further. In these cases, the dew point is identical among the three because dew point is absolute moisture, independent of temperature or anything else. Now, if we look at three same samples at 50% humidity, right? So 50% saturation in each one, now you can see the dew points change pretty significantly. So at 50% humidity in a warmer sample of air, you've got a lot more moisture because there's more storage capacity. You'll find in the Northeast or even the Midwest during the winter when it's fairly cold out, the relative humidity is probably 75, 80, even 90%. Now, that doesn't mean there's a ton of moisture in the air. It just means there's a little bit of moisture, but that air is so cold you can't store a lot. So we're closer now to that lower end of the scale, right, where a little bit of moisture means a lot. These three values, again, ascending, show that on a warmer sample, even at the same relative humidity, you've got a lot more capacity, right? So there's a lot more moisture. It's going to condense out a lot quicker. This is a chart some of you may have seen. It's called the Ashtray Psychometric chart. Gives a ton of information. Back in the day, which is actually not that long ago, if you're doing a mechanical system calculation, trying to figure out a cooling system, you'd pull this chart out and plot a bunch of lines and figure out all your different cooling and dehumidification processes. What this is useful for at a glance is looking at calculating dew point based on conditions. So your vertical lines here are air temperature. Your curved lines are relative humidity. And then this line over here at 100% relative humidity is what's called the dew point. So if you annotate this here, if you find a random point on the graph, right, where the temperature and the humidity intersect, you come over to this point and you can see your dew point right there. So it's fairly simple. Now, as you go up in this, as your dew point increases, the scale on this side is a measure called humidity ratio. That's absolute amount of moisture, right? So more moisture, higher dew point. So you can use this chart. You can also go on Google and type in psychometric calculator or dew point or something like that. And there's any number of tools out there, many for iPhones and Android. So it's a little easier, but this is the way it used to be done. So I mentioned condensation happens on surfaces colder than the dew point. If everything's above the dew point, condensation never occurs. What we're going to discuss is surface condensation today, which is visible condensation on windows and other elements. There's a whole nother issue that comes up with wall assemblies where your dew point occurs somewhere within the wall. And depending on the materials and the configurations, you can have concealed condensation in that assembly. So this is why we use things called vapor retarders or vapor barriers, basically the same thing, to prevent that moisture from going through walls and reaching that dew point. It's a lot more complicated. That's a whole presentation itself, maybe for another time. But today we're going to focus on surface condensation only. And in particular, windows, doors, curtain walls, anything fenestration is generally the biggest risk in a building because you have the lowest surface temperatures. So for example, if you have a thermally broken curtain wall with decent low E glass, you're probably looking at about R2.4 effectively, looking at all the different heat transfer modes. If you get a really good window with something crazy like 4 panes of glass and multiple low E's, maybe you can get to R5, R6, but then look in the field of your wall. Let's say you have 2 inches of XPS or like 3 inches of mineral wool, you're at about R10. So it's much, much higher. This is starting to change, looking at things like Passive House, where your window R values can get into the 8 to 10 range. But for most buildings, the windows are going to be the most conductive element. This is just an example. This was actually a swimming pool in Connecticut, and none of the systems were designed taking into account that it was a swimming pool. So this is a system that would have worked fine in a lobby or an office building, but in a pool where the dew point is 65 degrees and the design temperature is 2 below 0, this thing would condense for almost the entire year. Similarly, this is actually not a pool. This was a museum building. It was only humidified about 40%. This is near Washington, D.C. But if you'll notice, the side lights here are fine, right? That's actually insulating glass with a little heating under it. These were single pane glass doors. So these things would just completely fog up because they were 20 to 30 degrees colder than all the surroundings. Simple case of somebody didn't take into account the application when they designed a fenestration and a door system. Another application, this is a pool, and you can see the walls are fine, the concrete block and everything is insulated on the outside, but even when the pool is not in operation, you've got a ton of moisture condensing on this. And this is a fairly decent system. It was thermally broken, you know, a good inch thermal break, low E glass, argon gas fill. Again, this would be fine for your office building, but at that elevated moisture level, you start to see these problems. Skylights are another one. We see this very often in institutional buildings. Skylights are more prone to condensation for a couple of reasons. The first of which is in a horizontal position. For much of the year, when you have clear sky conditions, you're tending to radiate more heat to the far off sky, essentially, which has an effective temperature that's very low. To illustrate this, this is, I think, one of the first thermal images I ever took. This was about 3 in the morning, so the car hadn't moved. But what you can see is that the top of the car is much colder than the underside because you've got this radiation that's coming off the car, off to the sky. Same thing with the surrounding conditions here. You're radiating all this heat off to the sky, which can drop surface temperatures by 5, 6, 7 degrees, depending on the conditions. Now, underneath the car, you don't have the same thing, right? This temperature scale is fairly narrow, so this isn't really hot. It's a span of maybe 15 degrees. But where you block that radiation to the sky, you don't have the same issue. The sides of the car that don't have as direct a path for radiation, similarly, you don't have the same temperature drop. Now, the other problem with skylights, you know, everyone always says, well, the skylight's at the top of the building and warm air rises. Now, that's true. I've heard that argument a lot. It's never actually played out in practice. But the reality is you have a certain amount of heat from a space. Spoiler surprise, hang on. You have a certain amount of heat from the space that rises up to the skylight, right? Depending on where all your systems are. Now, the dew point up here is going to be the same as it is in the space because the moisture, even if you have temperature gradients, the moisture is still going to travel up there. The problem is the heat lost from the skylight is at such a higher rate than the amount of heat that actually gets there. So yes, you have this heat rising, but once it gets there, you have way more heat loss coming out of it, results in a lower localized temperature. So if you're ever working on a project and someone says, oh, we modeled the skylight at 70 degrees, that's probably not the correct assumption because you're farther from the heat source and you have this imbalance of heat flows, which means your skylight is going to be a lot colder, but subject to the same moisture levels as everything else. So what determines interior moisture levels? It depends on where we are, but a typical residential occupancy, occupant respiration, breathing is a big part of it. It's about 0.2 pounds per hour for a person like me sitting here, talking, not doing anything strenuous, that can double, triple, quadruple for someone doing heavy exercise or manual labor. So you're churning out a fair amount of moisture just by existing. In a house, you have things like cooking and showering and hand washing, all that puts moisture into the air. Depending on where you are, outdoor makeup air can be a big one. I've investigated a lot of buildings in the South where people didn't take into account the makeup air coming into a building. So in Texas, for example, if you decide, oh, I'm going to double the amount of makeup air and get more ventilation, that's a tremendous moisture load to the space, and the equipment needs to be designed to handle that. And then last is artificial humidification. This can be done for a number of reasons. Very often people humidify residents for comfort issues or for health issues, since a very dry environment can be uncomfortable. If you have something like asthma, it can actually be dangerous. And then you have special use buildings like museums are maintained under controlled conditions for preservation. Swimming pools, again, by nature of the building, there's a lot of moisture in there. So there can be a lot of different reasons. Now for residential, you didn't used to see a lot of residential condensation issues on a widespread scale. And we are starting to see a lot more of those. We have been actually for years. And I'll go into a few case studies, but looking at conditions, this is for a typical New York City building. And the red line is we're at 7.5 CFM per person of outdoor ventilation in an otherwise airtight building. So even at that rate, you're at like 40, 50% humidity. This is over the course of January, February, which I can tell you from experience and common sense, a typical residential window will not do well at 50% humidity. If you drop down, the magenta line is 15 CFM per person. Your humidity goes down into the 30-20 range, depending on the outdoor conditions, much, much lower. And the reason being is you're diluting that moisture on the inside. You're bringing in that dry outside air and helping to drop the levels. So keep this in mind when we look at a case later when ventilation was not provided. The measures of condensation resistance. So there's a couple different ways that you can define thermal performance. U factor is probably the one you hear most often. If you're selecting a window to meet energy code, you're going to look down in your code wherever you are and say, all right, this is the type of system I have. This is a U factor that's required. Now, this is an overall heat transfer coefficient. So it takes into account heat transfer through the frame in all directions, heat transfer, including radiation across insulating glass, and combines that all into a single number. It's useful for figuring out heat losses and gains, mechanical calculations, energy code, but it doesn't really tell you a lot about the interior temperatures on the frame, which is what's really going to control condensation. As I mentioned before, if the temperature on a frame is higher than the dew point, you don't get condensation. So what you really need to look at is what are the surface temperatures on the frame at a design condition. Now this is tricky because a typical U factor is calculated about 0 degrees Fahrenheit, and that's standardized. But for surface temperatures, if you're in Seattle versus New York versus Miami, the outdoor conditions can vary quite a bit. There's a standard called AMA 1503, the CRF standard, you may have heard it referred to, and it's a test method for both thermal transmittance and condensation resistance. This has been around since about 1972, and it's a procedure for determining both the U factor and interior surface temperatures under prescribed conditions. Again, typically about 0 degrees with a wind blowing on the exterior of the specimen. The reason they do that is that wind on the outside increases surface convection and kind of pulls more heat away from it. So just like when you walk outside in a cold day, it might feel fine until the wind blows. That wind blowing across your skin or blowing across your face is going to tend to extract more heat. The same thing happens with a window. The way this test goes, for anyone who hasn't seen it, is you have a big insulated panel that you stick your specimen in. You've got a blower pushing air through flow straighteners, so you get a fairly laminar flow against the outside. And then you measure the different temperatures on the inside, and from that you calculate this CRF number. This is what it looks like inside the chamber. This is ATI in York, Pennsylvania. There's many labs like this, but this is your fan. These are your straighteners. This is wrestling a giant skylight mock-up into their test chamber. So the test chamber is basically cold on one side and warm on the other. The specimen goes in and is surrounded by an insulated panel. So what this means is that when you measure the condensation resistance of a window element or a door or whatever, you basically cut out your heat transfer along the side. So there's really no heat transfer going through the frame. It's all going through this thing kind of perpendicular. So it does not take into account frame losses like you would get in a real building. This is important, as I'll show in a minute. So again, insulation, lots of duct tape, as any good engineering study will include, and then a whole bunch of thermocouples on the inside of the window. The way the AMA standard works is there's several predetermined thermocouples on the glass in the frame, and then there's what they call a roving thermocouple that will try to find the lowest temperatures to use in the calculation. So there's a total of 24 of these. You take all these numbers, you manipulate them with a bunch of different formulas, and you come up with a CRF, or condensation resistance factor, one for the glass, one for the frame, one for the overall. Now, what's interesting about this test is that, and we'll kind of get into this, it's a single number. So it doesn't necessarily tell you exactly what's happening. But if you're dealing with one of these reports, looking at the report itself gives you a lot of great information about the performance of the window, where the cold spots are, et cetera. So the AMA standard has this table at the end where you've got temperatures and CRFs and humidity levels. The idea being, if you look at a temperature, and you can see several different cities along here, right? Look at an outside design temperature and a CRF, and it tells you don't go above this relative humidity. I will say this is a decent estimate. It's not perfect. Anyone who's ever done more than 2 building projects knows nothing's ever the same, right? So it's a very hard thing to standardize. So the problem, again, a CRF of 55, what does that mean? You know, if we say that there's an R value of 10 in insulation, that's pretty well defined. Or the surface temperature is 30 degrees when it's 0 degrees out, that's pretty defined. So the number itself is a little vague, and the way it's put together, it doesn't account for real world conditions such as perimeters, right? Your real window is not going to go into a block of insulation. There's going to be clips, there's going to be wood, there's going to be metal, all sorts of things around it. Air leakage is another one. This can significantly impact condensation resistance. So I did a study on this for an article I wrote, I think about 2005. And on the left side, you've got these different values from actual test reports, right? So this is looking at test reports of real window products. And then this is if we use the AMA table itself. So not looking at a test report, but saying, all right, I know this number, here's what I predict. So this window and this window, right? The horizontal one has a CRF of 57. By the test report, looking at the temperatures, it condenses at 31%. The curtain wall has a CRF of 60. It condenses at 24%. So higher CRF, lower condensation resistance. And in both cases, right, you're actually a lot lower in relative humidity. So you condense way below where that AMA table says, meaning that the actual CRF is a bit lower. Now, again, I don't want to say I'm trashing AMA. The reality is it's a very difficult thing to standardize something like this. So the CRF tables, you know, again, it's a good ballpark, but it's important to understand the limitations and to know when you get one of these CRF reports, don't just go by the number, look at the report, see what the temperatures are. And that's going to give you a lot more useful information you can apply to your project.
Hey, Sean, we got a question. If I
Sure.
can interrupt for a second. Bud Henson asked, is there a chart, graph, or anything that will allow a comparison between AMA 1503 CRF and NFRC 500 CR?
So as far as I know, there is not. I know the CR number, which you calculate that through window, is done a little differently. But as far as I know, there's no direct comparison between the two. I think the way that they're calculated makes it a little hard to put those side by side.
Thanks.
Yep. So again, talking about real world considerations, right? We looked at this hospital with massive condensation problems. They're humidifying to about 30% humidity for comfort, which is not crazy. That's not a lot of moisture, even in the Northeast. So the window they used, it was a very simple thermally broken system, decent glass. And in the tested configuration, which means you get a test report where this thing was up against the insulation, that test set at 0 degrees, we had a 38-degree minimum temperature. So we shouldn't have seen condensation. That was the basis for selection of this window. Now, anyone who's ever done a window wall system knows there's typically a starter sill. So now when you add in that starter sill, which is along the bottom, right? So this element here, to actually retain the window and keep it in place, you're adding more metal, you're increasing the amount of heat loss, and now your actual temperature is about 33 degrees, which is 5 degrees lower. It's a decent drop in performance, right? That's something to consider. Now, what they actually did here was they used an all aluminum starter sill with 0 thermal break. And you can see just visually, right? Green is warm, purple is cold. Once you put that all aluminum sill in there, it completely defeats the point of your thermal break. And now you're 15 degrees colder on the inside than what the test report said. And this was the result. So probably a 1/4-inch device would build up on these sills because they were so cold. And the problem with this, you know, if you condense just a little bit on a window, generally it dries out when the sun comes out. When you're at below freezing temperatures, this ice will stay on there for a very long time. And this is a huge issue. I'll get into how we fix this in a little bit. So on the design side, how do you analyze condensation, right? The CRF alone is not enough. It's just a number. The CRF report, that's a great thing to use because it tells you actual temperatures, but it's only useful if you're at 0 degrees because those are the conditions of the test. So to get around this, there are many software tools available. Therm and Window are probably the most common. These are free. They are well maintained and documented. People have used these for probably 20 to maybe even 30 years. And these are simple. Therm is a simple finite element tool where you draw your shape out or you trace from an underlay, you assign materials, you assign boundaries, and it calculates the 2D heat transfer through one of these assemblies that you define. So from this, you can get interior surface temperatures, exterior surface temperatures. You can evaluate, let's say you're doing a window design, you can evaluate what happens if I put a receptor in here, right? What happens if I actually put this in a real wall? How does that affect things? You know, this is another example. This was looking at a storm window in a museum where we take our window system and now we're not just looking at the window, right, itself, but we're including the surrounding conditions. We're adding pieces on the outside. We're getting an overall picture of what's happening, which is way more than just a simple number or a simple surface temperature. Associated with this is a program called Window. This is a very useful program. I probably use this at least once a day for the last like 15 years. This program allows you to construct virtually insulating glass units. So in this case, you've got 3 layers of glass, you've got 2 gas fills, and you can see here, this is a low E coating. And this program uses something called the International Glazing Database, which basically when a manufacturer comes up with a new low E glass, they test all the properties and they send the information in, and that goes into the database. So you want to find, you know, Virecon's VE12M coating, it's in the database. Different gases, it's all in the database. And this will give you U factors, solar heat gain coefficients, interior, exterior surface temperatures, visible transmittance, pretty much anything you could want. Associated with this is a program called Optics, which is a little more advanced. That lets you kind of toy around with individual layers, make custom layers. So let's say you wanted to use, solar band 60, right, as a low E coating, but the database only has it on clear glass. You want to do it on laminated glass. So in optics, you can actually put those layers together and combine the properties and then come back into here and put that into a real unit. So this is a very, very useful tool for glazing design. Once you've done or created an IGU here, you can transfer that back into Therm, into a window frame, and put the total package together. What you can also do is if you want to simulate, so if you're looking at NFRC 100 for calculating U factors, you can go through and define all your different sections in Therm, export that data, and then import everything into window and put it together. So now you're virtually recreating a hotbox test for a window. And you can change things like the temperature parameters, anything having to do with the glass in the frame, and you get an overall value for the window. You can also get into more advanced things. We tend to design in 2D, or at least we did for quite a while, but buildings are 3D things. When you get to very complex constructions, this was a kind of a lens-shaped skylight over a mall in New Jersey. We have to go into 3D analysis to look at how all these different things interact. This is using a program called ANSYS, which is kind of a workhorse finite element simulator. Similar condition, this is the point supported skylight where the glass was actually hung using these support points. And as you can see, it's a lot more complex than the 2D, but the physics and the assembly, everything is basically the same. You're just adding a dimension. The complexity is much higher. When you go from Therm, where you don't need to know a whole lot about finite element theory, into something like ANSYS, this is a lot more of a specialty thing, right? You're not going to download ANSYS and toy around with it on the weekend, and do some calculations as you could with Therm. But there are applications where you need that extra level of calculational horsepower, we'll say. Then something else we're getting a lot more into, especially with very complex designs, is using computational fluid dynamics. Now, what this does is it combines 3D heat flow with 3D airflow. And where this is useful in this case was curtain wall areas where you had a blower that was directing air onto those surfaces. So this type of software analysis, which is a whole nother level of complexity, allows you to simulate that airflow and the resulting effect on the window itself. So are you going to do this for a typical office building? Probably not. But when you're working on the National Air and Space Museum or the Smithsonian or some crazy custom system, you might need to go to that level. This is on the inside of one of those where we're mapping out temperatures and other things. So you can see on this one shot over here on the right, this is where your warm air is directed most closely. And then here, your airflows are a little lower, so your temperatures change. Again, not a run-of-the-mill analysis, but it's something that the computational abilities are definitely there. This is looking at just a 2D cut through a model. This is a residence where the owner wanted 50% humidity because they were displaying artwork. So this is looking at outside doors and the effect of air curtains trying to blow air over there and counteract the condensation risk. So the big advantage of these analysis tools is that going in and doing an AMA 1503 test or a real hotbox test is very expensive. It takes a long time and you're fairly limited in what you can do. When you come into an analysis, right, let's say you do an AMA test and you say, I want to know what happens at 5 different temperatures, that's like 3 days in the lab. If you do a model in Therm and you want to evaluate different temperatures, it's 20 minutes of simulation time. So what we typically end up doing You know, if we're looking at evaluating performance as something we have a test report for, is you do your analysis in therm or ANSYS or whatever you're doing, and then you reality check that against your AMA test. Now, once you've gone through and confirmed that the model is really reflecting your test results, it gives you a bit higher level of confidence to say, all right, I'm going to use this model now. I'm going to change all these parameters and see what happens. So we often go into these cases where we're looking at field testing for condensation resistance. And one of the tools that ends up being maybe not the most useful, but one of the most useful is infrared, right? Thermal cameras. So in this case, this was a 80-foot tall atrium. There's this big wooden construct in the middle that had to be kept between about 30 and 60% humidity, because the boards would literally warp and twist off if they got too dry. This was a heated curtain wall system. So there's actually electric resistance cables running through this. And the intent was, let's keep this thing warm enough so we don't condense. You see moisture all along this central area where the crosshairs are, and going in with infrared took all of 30 seconds to realize they lost a heating circuit, right? Temperatures aren't there. So because surface temperature is the determining factor for condensation, the ability to look at that and to see temperatures in infrared is very, very important. We often see condensation due to air leakage as well. So you've got a very good system with good performance with terrible perimeter conditions. And now when it's 30 or 40 degrees out and you're blowing cool air around it, which is what you're seeing in this thermal image, right? Thermal on the right and photo on the left, you're cooling down those surfaces and condensing. So again, visualizing where the problem is. This is an interesting example. This is a university in the Northeast. We were working on this project. We had to do condensation testing of a storm window assembly. And in this case, the original schedule called for the mock-ups to happen in February, basically the coldest point of the year. And we were just going to install this thing and monitor it for a few weeks. This was 2008. The 2009 recession hit, everything stopped, and the schedule shifted to the point where the mock-up had to happen in July. So what they did, and again, not going to see this every day, but just to give you a sense for what can be done in a building, this was a refrigerated chamber. So it was about 3 inches of polyiso insulation built over framing, and they backed up a liquid nitrogen tanker to this thing and cooled the whole assembly down to about 7 degrees Fahrenheit, which is a design temperature, and kept it that way for the 3 or 4 days we needed to do our test. This was not cheap. I want to say that the liquid nitrogen alone cost something like $10,000 a day, but it was also a 9-figure project. So in order to confirm things, you know, the mock-up and everything, it was worth it. Again, not going to do this on a typical condo or office building, but for critical applications, it kind of shows what's possible. So those are kind of the basics of condensation, right? Why it happens, how you measure it, et cetera. So now taking those concepts, I want to go into a couple of different case studies where we looked at condensation issues and why they happen and how we resolve them. This first one is an uninsulated masonry building from the 60s. It was a humidified, was a library where they humidified the top floor as part of a renovation because it was historical storage, right? Archival storage. They went to about 40% humidity. The drawings included storm windows on the existing windows, a very good curtain wall on the 3rd floor where everything was, so right here, you know, these windows, they installed storm windows on the inside. Drawings had about 20 pages of millwork and 1 mechanical drawing and 1 curtain wall sketch. So they really focused on the interiors here, not on what was happening on the outside. So we get called in. We were doing some other work at the school at the time. And this is what we see on the inside at these storm windows. So the storm window itself, insulated glass. The outer window is single pane steel frame windows. And these things were just sweating like crazy. In some cases, there was frost on the windows. The design temperature for this area is 10 degrees below zero, actually. And the day we did our investigation, I want to say it was close to 15 below zero. So this is a real cold environment we're talking about. Again, looking back, you've got these heating grates underneath these, but the condensation is not happening on the storm window, it's happening on the existing window. So through some smoke pencil testing, right, trying to find air leakage paths, we find that the corners of these windows are not actually sealed. So the storm window is not actually sealed to the frame at these corners. And along the bottom, right, you can see this right here is that grill at the bottom. So there's no way to seal across the bottom of this. So you've got a big gap on the underside of this. And what happens, you throw this storm window on, right? You seal it a little bit, but it's not fully sealed. And now that heat from the interior can no longer get to the outside. So your existing single pane window is now within a few degrees of outside temperature. Any air that gets into there, it's not going to take much. You know, when the window here is at 5 degrees Fahrenheit, even a few percent humidity is enough for condensation to happen. Now, the big problem with this is condensation occurs in a sealed space where you can't access it. So it shows up, it eventually drips off, it wets the floors, and over time you start to get that white staining on the glass from repeated moisture exposure that you'd have to pull the storm window off to fix. So this was a simple matter of sealing and venting, right? So you seal around this window, you keep most of the moisture from getting there, and then you vent the original window so that you're able to drain that moisture to the outside. And that's a fairly common approach when dealing with storm windows. For the curtain wall, this is a different story. So this was Wassa's HP wall. It's got a 2-inch thermal break, triple glazing on it. Very good system, very low U factor, meaning high performance. And this is what we saw when we showed up. So this is ice and frost all over this thing at the design temperature or around it. Now, the interesting part is we were talking to people, part of any investigation is you go and you talk to the people, right? Who works at the building, what are they seeing? And everyone on the bottom floor, the one floor down, said ever since they did the renovation, we get all sorts of leaks from the curtain wall, but it only happens in the winter and usually in the mornings. So it turns out this thing would freeze overnight, collect moisture, southern exposure, you get the sun coming in, it would melt everything, and all this water would literally drip down into the space below. And that cycle had just been repeating for weeks and weeks before we got there. Now, the issue here, again, this comes down to what you get versus what you think you're getting. This was a test report. This was the analysis of this system, looking at surface temperatures as you would get them from, the factory test report without taking into account the perimeter. So 51 degrees, this was about a 50 or about a 44 degree dew point. This should have been plenty. This is what they actually got. So you have the existing window system, the existing curtain wall system with this big non-thermally broken steel angle at the bottom, at the top of the existing curtain wall. And then you plop your system over there. So now you've got a huge thermal bridge that completely ruins the performance of what was installed. And that means that at design condition, you're now freezing temperatures on this and you're freezing condensation. So they probably paid $250 a square foot for this curtain wall, and they got the performance of something you could buy at a hardware store. The eventual solution there, there were many potentials we investigated, but their eventual solution was to move the archive away from exterior walls, put it internal to the building, because they said that the disruption to the building to rip out this curtain wall, to rip out the storm windows and everything would just be too much. It was easier to actually move things around. So this is a good case study in careful planning, because a solution is often just not a practical one. This is a condominium in the Northeast, non-humidified, typical run-of-the-mill residential. And this is one of the first projects I worked on when I joined the company. It was an EIFS building, barrier EIFS, right over drywall, massive leak issues, massive problems. And we reclad the entire thing with a drainage EIFS system, put in new windows, doors, a complete rubberized asphalt air barrier, since at the time Massachusetts required that in the code. And this was intended to solve both the air leakage and code issues, but primarily water leakage. As part of this, we put in new heat pumps. We worked with a mechanical engineer to design those heat pumps. The infrastructure of the building was such that there was a closet with a 220 volt outlet, and that was it. So a packaged heat pump was really the only option we had. So we go through and we do this whole thing. It's a very long sordid tale, as many construction projects are, but we pass our water tests and our air tests and everything's great. And the first winter, we start getting calls from people. They said, all these new windows are condensing all over the place. We never had this problem before. What's going on? So this is a view of one. It's a horizontal sliding window. You can see condensation all over the glass and the frame and the sill. This was an example someone sent us first thing in the morning where you've got frost and ice all over these. And these were pretty good windows, thermally broken, good glass, no reason to expect them to condense. So we start by doing an analysis. This is a therm model looking at site conditions and the actual window and the surrounding perimeters and what we get for conditions. And we're showing about 44 degrees, even on the coldest day of the winter, which is way above our dew point, which is about 30, 37 and change. So one thing we had looked at was the use of window shades. You often see they advertise energy efficient shades or energy efficient window blinds. The reason they're energy efficient is because when you drop this thing, you block interior heat, kind of like a storm window, from getting to the outside. And now your window surfaces end up being colder. So you're reducing heat loss, but at the expense of the window being colder. And now you've created this cold surface where you're more likely to get condensation. This is a tricky issue because a lot of people will look at this and say, so you're telling me I can't have window shades? Well, it depends on what's happening and what your humidity levels and what your products are. But I've seen a lot of cases where drawing the shades will lead to an issue like this. Now, if we do the analysis and we add the window shade on the interior here, right? So that's this line right here. We create this captive airspace, and you can see our temperatures drop by 7 to 10 degrees, which makes sense because we've added this insulating air gap, right? And now we condense at a lower temperature. Still not what we'd expect though, right? Still not low enough to just condense all the time. So when I mentioned the mechanical system, we had an air barrier requirement, which meant that this building needed to be very, very airtight. There was a dedicated barrier that we had to put in here to keep air from going in and out. This is commonplace now. All the I codes, Ashtray 90.1, it's everywhere. But at the time, it was fairly new. So when we did this, the first thing that we said, being a mechanical engineer by background, we looked at this and said, hey, if you're making this building airtight, you've got to provide mechanical ventilation. Because up until now, the code relied on basically, keep in mind, this is about 2004, the code would allow you to use operable windows, and they rely on what they call incidental air leakage. So whatever air just happens to come in and out, that was enough for ventilation. Think of getting in your car on a cold morning. You get in the car, you turn it on as it's warming up, and just the act of you breathing, within 2 or 3 minutes, you fog up the windows, right? Because it's an airtight construction, the car is relatively airtight, and you build up moisture in there, and the windows are cold. So fairly simple. This same thing happens in a building. So if the building is too airtight and you're not changing the air out, the act of someone just breathing over a couple of days will bring relative humidity levels into the 50, 60, I've even measured 70% range, which is way more than any of these residential systems are designed to handle. So the trick here is we needed mechanical ventilation. But at the time, this was not on many people's radars, so it was hard to find a heat pump with fresh air capacity. Now you get systems with energy recovery that are very efficient. Back then, it was the equivalent of one of those window air conditioner units with a little slider that says fresh air open, and it's a hole on the outside. That's what we were stuck with. So because of this, we designed this little sticker that basically said, keep the fresh air open, right? If you shut this, you lose your ventilation, you have a problem. And sure enough, every unit we went into with a condensation problem, the owners had shut this thing and said, well, you know, I thought it's more efficient to have it closed. So apparently they didn't notice the sticker. It is worth noting that even though this is a fairly inefficient way of doing it, because there's no energy recovery, utility bills were still less than half of what they were before, even bring this air in. So this was the first example I had of this issue. It is something that plagues us today. I looked at a building in Brooklyn 2 years ago with the exact same problem, right? Brand new windows, everything met energy code, zero ventilation, because you can rely on operable windows for fresh air. Does it work? Absolutely not, because nobody's going to open their window in December or August. But the codes have not quite gotten there yet. They're close. For high-rise construction, at least, there are requirements for this, but this is a case of the envelope and the mechanical systems just weren't designed to mate together, right? So a holistic view is always needed when you're looking at these problems. Next is a Skylight Issue. This is a museum in the Northeast that I cannot name. Someone may recognize it, but it was a large addition to a very prominent museum, and they had a series of skylights in all these different galleries. And they had massive condensation problems, just all sorts of dripping coming down from these things. Now, I mentioned before, the issue with skylights has to do with both radiative heat losses, but also just heat balance, right? So in this case, you've got a lot of heat leaving your skylights, and you've got a linear diffuser all the way down here that somehow needs to deliver enough air to the skylight to balance it out. Obviously, that wasn't happening, right? The heating system was just not designed to actually warm those skylights. So looking at a thermal analysis of these systems, even assuming it's 72 degrees on the inside, the skylights themselves did not have enough performance, right? You couple that with lower temperatures due to lack of heating, and then also a window shade that comes over the inside of this and blocks it. And now you've got major condensation issues for a very significant percentage of the year. This is a similar, actually different, sorry, this is a flat skylight between the galleries. And again, analysis shows that you're condensing on this thing at the design temperature. So at a very basic level, the system itself in the ideal configuration couldn't do it. Now you combine that with this little configuration here. I will animate what the designer intended to happen, which is the air comes out over here, takes a left turn, comes up, warms the underside of the skylight, and then returns. This is a skylight lay light assembly, so there's a gap between them. The reality is that air shot straight across to the return. Your actual temperature in here was probably in the 50s, and now you would condense on the upper glass like this, and then you would drip down and create puddles of water on this lay light. This was a sealed space, so you had to literally cut holes in the walls to go in there and clean it out. Again, poor design, right? It was a poor design because the skylight itself did not have capacity to handle condensation, even in the ideal case. But you combine that with perimeter conditions and not understanding how the mechanical system is going to actually keep this warm, and you end up with probably a $4 million lawsuit on your hands. The solution here, go back a couple slides. So you can actually see this little silver thing down here. The solution was to run heat trace, so electric resistance heat trace around all these skylight components to provide that warming, even when that blackout shade was closed. And there was so much heat trace up there, it created a local localized warm environment that protected the glass as well. And then in this other case, they kind of modified the mechanical diffusers, try to get more air directed up towards the skylight and use a mechanical system, because your supply air coming out is 90 degrees. It's pretty warm. So that's plenty to keep the skylight warm. You just got to have the air pointing in the right direction. This is another condominium in Rhode Island. This is a good example of when the CRF works and when it doesn't. They had some issues with ventilation, more likely the lack of. So the interior humidity was about 30%, but it wasn't terrible, wasn't too high. What they did is they kind of mashed a couple of systems together. So they used curtain wall framing. This is a typical, floor-to-floor module. And then you've got a fixed window and a double hung window and an insulated panel, all combined into the same thing. On the interior, you had all sorts of condensation issues. The black there was apparent mold growth. The lawyers tell me I'm not a mold expert, so I can't actually call it mold, but probably what it was. You had condensation all over these things, even at mild outside temperatures. So September, October, not the dead of winter. Again, not what you want to see in a window. Now, what happened here, we looked at all the documents, and the designer looked at the CRF data for all of these individual components and used that chart from the AMA standard and said, hey, these systems should be enough, right? Everything says these are going to work, which was true individually. But now you've taken these components and stuck them inside a curtain wall frame, or you've taken your fixed window and molded up against a double hung window with a solid piece of aluminum to hold them together. And all of a sudden, the individual performance no longer works. What they really would have needed was a test of the composite assembly. Now, this was a custom system, and they didn't test the actual assembly, so you never really got to the real performance. It wasn't until the cold weather hit that you found out, wow, doing all this and putting all this together didn't really work. Again, the poor ventilation was also an issue here, and that was actually what they ended up doing. They ended up increasing the mechanical ventilation, and that dropped humidity levels low enough to reduce the condensation to a reasonable level. So the cost of ripping everything out and putting in new windows was pretty significant. The cost of increasing or improving the ventilation to address that issue ended up being a lot more economical and effective. Now, another problem that you might run into is condensation within insulating glass units. You might have heard the term fogging. That's often how it's referred to. This is where you have condensation between the lights and glass within your sealed unit. This was my old apartment in Boston, regular run-of-the-mill Home Depot vinyl windows, never really had any problems, but once you get to about 20, 25 years old and the seals start to go, you end up with that condensation issue. Now, the way this works, an insulating glass unit is composed of 2 or more lights of glass. You've got a structural silicone seal that holds things together, and then your primary seal, which is an air and vapor seal, on either side of a metal spacer. That spacer is filled with desiccant, which absorbs moisture. So over time, even these seals, they'll eventually let moisture in on a long enough time frame. This could be due to, in a new unit, maybe the seals were damaged or not done right. Maybe the unit sits in water, right? We've all heard about weeping a glazing pocket. That's very important, because if a unit sits in water, eventually it wicks the moisture up. Or it could be just the unit gets too old, right? It's been in the field and the seals are just not doing it anymore. So typical operation, you get a little bit of moisture in here, right? And some of that moisture is going to get absorbed by your desiccant. That's the idea. The desiccant pulls it out of the unit and keeps the moisture level in there low. Now, once that desiccant reaches its storage capacity, the moisture's got nowhere to go, and it will generally condense on the coldest surface, which is the outer light. Similar to that issue of the storm windows at that museum project, once this happens and you get moisture in the unit or you get staining, there's nothing you can do about it, right? You start getting, the glass becomes obscured. It may become translucent. Sometimes it's enough so that you actually can't see through it, but there's really no way to fix one of these units. If you've ever had to diagnose this, we looked at a couple of buildings where we actually took units out and submerged them in water and then pushed down the glass, and you saw where the bubbles came out, right? You found the holes. If it's a different issue, if it's just a long-term issue and you're trying to figure out if these units are close to failure, there's a test, I believe ASTM has a standard for it. It's called the frost point test, where you take an assembly that moves a piece of dry ice closer to the glass and you see where moisture condenses, and you can figure out if you know the temperature here based on your cold assembly is, let's say, 5 below zero and it's 70 degrees out, you can figure out the dew point of the unit. And from there, you can assess how close it is to failure. This last one, this is a private residence in the Northeast. This was a private owner, had a fairly decent art collection. His daughter had asthma, and as a result, he wanted humidification for occupant comfort and health reasons. The architect wanted steel windows, which, if anyone has ever done this, even the thermally improved versions, the performance is not very good, right? It's a solid piece of steel, which is highly conductive. And even at 30% humidity, they had massive condensation on pretty much every window in the house. This results in water damage on the interior sills. A lot of the drywall ended up with problems. Here's a case where you have frost and ice building up on the windows. Same thing in the door sills. So this diffuser here is blowing warm air straight up, but it doesn't do anything for your sills out here. So you've got highly conductive elements combined with humidification. So we looked at this just as a thermal analysis, and our analysis showed us that on the interior here, you would expect condensation for probably 20–25% of the winter, depending on the season. So we put together this graph looking at your actual risk based on the outside temperatures and the model results. This is a useful analysis because if you do a steady state model and you say, wow, my steady state shows condensation, is that an hour a year? Is it 2 hours a year? Is it 100 hours, right? You need to assess the risk. So the primary issue here, this was a lawsuit that got dragged out for quite a while. We came in and the architect kept saying the same thing. I've done this 100 times. I've never had an issue. Well, they'd never done it in a humidified building before. So now the architect was blaming the mechanical engineer for humidifying, and the mechanical engineer is saying, I told you it was going to be humidified. You used the wrong window. And anyone who's ever been through litigation knows common sense, logic, and reason all goes out the window, right? It just becomes a screaming match. So everyone ended up paying a little bit on this one, but it was a good lesson, I think, for a lot of people to see you don't expect a major condensation issue in a residence. But when you have the right combination of factors, being a humid environment, a highly conductive window, all these things line up to create a problem. So, like I said, the solution here was not a very easy one. They eventually, to be perfectly honest, I'm not sure what they ended up doing because everything kind of fell apart after the lawsuit. But ideas were, replacing the windows, which that's not a great option. Adding heat trace or air curtains, which is very difficult to do mechanically. Reducing humidification levels. If you ever try to tell someone who spent $20 million on a house they can't have something they want, obviously it doesn't work. These people, to their credit, paid a lot of money for the house to have very specific properties. So in this case, I should probably follow up on this one, but there was not a lot of good options, right? And it highlights the need to really look at this stuff ahead of time and try to catch this stuff in design, because once things go into construction and operation, everything becomes much more difficult. So what are some remediation strategies, right? Ideally, if you're designing a building, you're going to do the analysis or hire someone to do the analysis or get a manufacturer to look at something. And let's make sure that we've got the right products and the right configurations. For buildings where either existing or maybe high humidity buildings where you've got very high moisture levels, especially in colder climates, often you end up with active systems to control the condensation. This is an example of an air curtain. This is a swimming pool in Connecticut. And you can see you're blowing air down and there's no condensation right below the air curtain, which is good. A few feet away, you have a problem. So is an air curtain a reliable solution? It can be, but it also requires a lot of coordination between mechanical and architectural to make sure that you're covering the entire areas. I mentioned heat trace. This is a museum we looked at in DC, where you've got a fair amount of condensation, not terribly high humidity, but there were issues with the windows. And in this case, this is a mock-up. It didn't actually look like this in the end. You have an electric resistance cable, kind of like what you use for snow melt, going around the inside of the window to deliver heat directly. This is kind of the brute force approach, right? This isn't saying I'm going to do a passive system with insulation. This is saying when it's cold, I'm going to throw a bunch of heat at the window. This is similar. The cables were eventually concealed, but they used a trim cover on the inside to hide that heat trace. And this ended up being the best option, much better than tearing out a bunch of windows and having to do all that renovation work. This is another hospital. This is that hospital I showed originally with the heavy frost in the window. And this is part of a mock-up monitoring system where we put on the heat trace. There's no trim or anything here, obviously. And we were looking at monitoring temperatures and confirming that the heat trace did its job. So this is a comparison. This was without the heat trace on the left side, and then with the heat trace on the right. The silver cover is concealing that heat trace cable, and eventually that became a painted aluminum trim. And this mock-up was able to show, yes, this system does work. The mock-up is very important because the only thing worse than having a problem in one of your building designs is trying to fix something and having that not work too. So always need to do a mock-up, especially for something like this that's very custom. Going back to that museum project in the Northeast, this was the heat trace on that skylight above the level of your window shades. Again, dumping heat up there, brute force approach, but it beat all the alternatives. In most of these cases, the heat trace we actually have being controlled by interior surface temperature sensors. It's easy to say, oh, we'll just have it turn on when it's cold out. But we found that the difference in control methods is a factor of about 7 in power consumption. The reason being, there's so many different things that come into heat loss in one of these systems. You might have a system on the south elevation that's in full sun for most of the day. So even though it's 10 degrees out, the window is warm enough. So you want to control to what the temperatures actually are. It's also worth noting that it sounds like a lot, electric resistance heat, et cetera, but that one window in this particular case, the total amount of heat being delivered here was maybe about 200 watts at maximum power. So, it's like running a couple of light bulbs for a few hours. So it's actually not that bad. Again, it is a very complicated system. You don't want to rely on this, but sometimes you have no other options. So a couple of closing remarks. There are current standards for condensation resistance. Some of them are misunderstood. Some of them are misused. All of them have use. It's really about understanding what information is being presented in those documents and how you can apply that to your specific project. Changes in building tech and how buildings are built, specifically in terms of air tightness and ventilation, have led to a significant increase in condensation problems. The issue of having low ventilation combined with, poor windows and condensation, we looked at a job, this was maybe 2006 in Santa Monica, California, which is not the kind of place that you would expect to see condensation on windows and doors, especially in a residence, but similar to what we've seen in the Northeast, the humidity just got too high, right? That ventilation wasn't there. So a case-by-case analysis is really what you need to do. And we have gotten to the point where there really is no one-size-fits-all solution because of the staggering breadth of the whole industry and what people are doing. Every project really truly is different, and you need to look at things on a basis of what's right in front of me, what's at this building. Whatever you did in the last building, you can learn from that, but you probably can't apply it directly. So that is everything I have for the slides, and I'm happy to stick around and answer any questions or discuss anything people might have.
Great, Sean. Thank you very much. I've had a couple of conversations recently about fourth surface low E coatings and the potential there for increasing condensation risk. Have you seen that occur or have experience with that?
Yeah, so I haven't seen it occur directly, but the way that works is you've got an insulating glass unit, and in general, you want your low E coating on the #2 surface. I've heard people still talk about they want #3 low E so that you reduce heat loss in the winter. But the reality is, if your low E is here versus here, the U factor does not change. It's all about solar heat gain. So this is a typical unit. Now, if you add in what they call room side low E on the interior, you're able to reduce the U factor and to some degree solar heat gain even lower. So you squeeze more performance out of the unit. Now, this coating has to be what's called pyrolytic or hard coat, meaning it's really embedded in the glass, right? Not the same performance as you get here, but you can get a good boost in performance. The downside is by reducing all that heat transfer, that means that your surface temperature here goes down by 5, 6, 7 degrees. I have seen, we're working on a job right now in a swimming pool. It's a residential pool building, and they wanted to use room side low E. And in a typical configuration, that would actually be enough to cause condensation, a couple of degree drop, right? They were blowing 100-degree air at the glass, so it didn't matter. In a residence, you know, if you're well ventilated, it's probably not going to cause a problem. If you're borderline, or if you're one of these cases where the ventilation is poor and you have these high humidity points in the winter, that temperature drop could make a difference. So like everything else, it's certainly got benefits. There's a lot to be said for it. It has to be done in the right application, and it has to be matched to what's happening with the mechanicals. So on that note, one of the big things in the industry right now, everyone's heard about passive house, and the reason passive house works so well is because the mechanical systems are finely tuned to the building enclosure design, both in terms of heating, cooling capacity, and also air tightness. So if you took the mechanical system from your house and put it into a passive house building, you would overheat and suffocate in like 20 minutes, right? Just like if you took a passive house system and put it in your house, it would be freezing in the winter and too hot in the summer. So you have to match these things together. And it's a tough one because a lot of people still design in boxes, and the mechanical engineer does their design based on assumptions, and the enclosure guys and the architects do other things. We are really getting to that point where if you want to push the envelope, if you want the high performance out of everything, it's all got to work together, which means we've all got to work together.
I don't see any other questions in the Q&A window. But if anybody has some, they want to drop in there real quick, we can try and get to them. But thanks, Sean, for your presentation this evening. That was great and really informative. We appreciate having the ability to reach out, across the country.
Yeah, no, happy to help. I appreciate the invite.
I saw a raised hand, but I don't actually know what to do with that. Maybe it was an accidentally raised hand. Oh, there's the Q&A. Cliff asks, what's your background? So you said you were a mechanical engineer?
Yeah, so I studied, so originally in high school, I thought I'd want to be an architect. And then all these schools required a portfolio I didn't have. So I said, all right, my dad was an engineer. Maybe I want to be a structural engineer. Then I shifted towards mechanical. Then I almost got a job in computer tech support because it was the only thing I could find in New York. And then I followed my girlfriend to grad school and found SGH. And it's an interesting one because what I do now combines aspects of all of my interests. And in our office, so I run the building tech group in New York, which is about 21 people right now. And I think 10 or 11 of them are mechanical engineers. So, and it just kind of happened that way. But yeah, I didn't know anything about this field. And now looking at it, I can't imagine myself doing anything else.
So it turns out Cliff was actually asking about the crane in the picture behind you.
Oh, background. So this is a new construction. It's a addition to a hospital on Long Island. So on the left side is an old 1970s curtain wall. We've got to figure out how to tie into. The background is the superstructure, and it just seemed like a cool picture because there were two tower cranes kind of competing with each other back in the fog. So yeah, I have a host of other office space related backgrounds and other things that I've collected over the whole COVID thing, but this is just the current one.
Yep.
I do see a question here about ERVs helping with moisture levels. So that was Tim Quinn. Yes, an ERV would absolutely help. It depends. Pacific Northwest, you might actually be better with an HRV, which does not have a moisture component to it. So the ERV will recycle both heat and moisture. So depending on what's happening inside, if you're trying to dilute moisture, the ERV might not necessarily do that because some of the moisture gets recycled back in. So I know in the Northeast, we've had, done a couple of small jobs with spaces, high humidity, and we've used ERVs to take care of that. So rather than heating the air and bringing it in and then dumping it out, you're recycling that heat, but you're using fresh air, so you're diluting the moisture.
Right.
If you go with an ERV, depending on the efficiency and how much latent turnover you have, right, how much moisture you recycle, it might not reduce moisture levels by enough to make a difference. But these are the kind of things, again, with a passive house design, you've got to do that because a typical apartment building in Manhattan right now is if you're ventilating at all, you're bringing in a bunch of outside air to the corridors, and then you're dumping that air straight out the roof on your kitchen exhaust and your bathroom exhaust, and the heat is just going nowhere.
Yeah, we've had a trickle vent requirement in Windows for a long time that I think has just dropped out of the code in favor of actual ventilation.
Yeah. I mean, trickle vents are tough for a lot of reasons. Often you'll find these window manufacturers say, "Oh yeah, we can put trickle vents in." They end up being holes, and they end up turning into leaks. I know I mentioned in New York City, there's provisions in the mechanical code for buildings above a certain height. If you have more than a certain amount of exhaust, you are required to ventilate mechanically to counterbalance that. So they're recognizing, again, it's December, people are not going to open their windows. And I don't know if it's Texas, there's something else recently I was looking at where depending on the air tightness of individual apartment units, that dictated whether or not you needed to have mechanical ventilation. So if you're in a super airtight unit, you need mechanical ventilation. If it's a leaky unit, which the code also shouldn't allow, but if there's enough incidental air leakage, that can be considered your ventilation air. But everything is going the route of controlled. It's just with an airtight space, there's no other way to do it. But if it's done right, if it's done efficiently, no problem.
We were talking at MH about if there are sort of diminishing returns to airtightness as you get, down below, 0.02, like if you get to 0, like, is that as beneficial? Or, if you add R value, you have diminishing returns in your energy.
Yeah.
And there's got to be some drop off, but I wonder if it's as dramatic.
Well, it's funny because we do a lot of testing for New York City public schools and air barriers.
Mhm.
And for a while, they would want you to do the whole chamber test, basically a field version of 2357, the air barrier assembly test.
Mhm.
And I kept telling them, guys, I go out there, there's holes, there's all these other things. Let's look at it this way. If I tell a contractor, well, your test is supposed to be 0.02 and it was 0.03, you have to fix it. They can't do anything with that. So go in, do a qualitative test and say, here are the holes, plug them up. And I would say in 90% of cases, you plug up those major air leakage pathways and you're fine. 0.1 versus 0.05 versus 0.06 and whatever. At a certain point, it's just the energy loss that you're looking at from uncontrolled air leakage is just so low, that it doesn't matter.
Yeah.
So, it's like everything else. You got to be careful of the pendulum, swinging too far the other way. And it used to be, just crack the windows and all the holes and who cares? But the answer is not, let's go to the other end and hermetically seal every building and spend 10 times more, to get to that last 2%. No, the answer is somewhere in between.
All right. Well, I don't see any more questions in the Q&A or the chat, and we are at 7:01. So thanks again for your time. Thanks for everybody for showing up. We appreciate having you here. We look forward to seeing folks again next month. And thanks again, Sean.
Yeah, no, my pleasure. Like I said, send me the list of attendees, AAA numbers, and I'll have my my marketing people throw together those certificates for the credits.
Great. Thanks, Sean.
All right.
Have a great day.
Good evening, everyone.